Hi, I'm Sangyun. In this video, I'll introduce our latest work in CBPR 2024, Spherical Mask for Point Cloud Instance Segmentation. Spherical Mask essentially overcomes two limitations of the coarse-to-fine-based segmentation. First, excessive box size estimation from axis-aligned bounding box, and second, error accumulation from the coarse detection to the refinement stage. In summary, Spherical Mask consists of two modules. First, the coarse instance masks are acquired by performing radial instance detection in spherical coordinate, where the instances are defined with their centers and the radius in each spherical sectors as in the top right figure. Secondly, the coarse instance masks are refined using radial migration module that moves each point in or outside of each spherical sector by referring the coarse instance masks. This is the flow diagram of the spherical mask. Given the point cloud, the 3D unit-based backbone produces default feature for each point and performs voting. Each vote is assumed to be on the surface of the instances, so the radial instance detection predicts offset to the center of the closest instance and the rays for each spherical sector. This decides the length to be considered as foreground in each sector. For example, if a point in a spherical sector is closer to the center than the ray, it is considered foreground. If the point is further from the center than the predicted ray, then it is considered background. This is for forming our coarse instance mask. This figure shows the details of how we generate targets for radial instance detection for each instance. We first divide instance into spherical sectors with preset angles. Then, the target for each ray is the distance between the furthest point in the corresponding spherical sector and the instance center. Here in figure D, the red sphere indicates the instance center, and each ray emitted from the center indicates the distance of the furthest point in each sector. The figure visually compares the axis-aligned bounding box from existing works in coarse-to-fine approach and the radial instance detection in signal-to-noise ratio. Here, the second column shows the ground truth axis-aligned bounding boxes of each instance. The third column shows the ground truth of radial instance detection using 9 spherical sectors. Fourth and fifth column show radial instance detection ground truths with 25 and 49 spherical sectors, and SNR here stands for signal-to-noise ratio. The larger SNR means fewer background points inside the coarse detection, leading to higher precision for the refinement stage and therefore improving the overall system performance. As can be seen, radial instance detection always show higher SNR compared to axis-aligned bounding boxes. Our second module, radial point migration, refines the coarse instance mask by predicting the per point offset in each vote. Essentially, it learns to move each point inside or outside of the predicted rays from the radial instance detection. Unlike existing works on coarse-to-fine approaches, we assume that the coarse mask is not always perfectly including all the instances and let the refinement module fix imperfect coarse prediction, which overcomes the limitation of the error accumulation. The final binary mask for each vote is generated by using the migrated point and the predicted instance center and the spherical sectors. Specifically, if the migrated points are inside each predicted spherical sector, they are considered foreground. In order to train radial point migration module, we utilize two losses, namely the misclassification correction loss and the sector cohesion loss. As their names suggest, misclassification correction loss only focuses on first positive or first negative samples as illustrated in A. On the other hand, the sector cohesion loss focuses on making true positive samples similar to each other's so that they learn potential features shared for learning instance mask. Splitting a loss into two functions with the coarse-to-fine approach has few benefits. For example, in existing works, all of the points are usually supervised with one focal loss or binary cross-entropy loss. However, as the learning progresses, the first positive or negative points typically become minor, leading to receive less learning attentions. Misclassification correction loss explicitly considers only first samples to guarantee certain learning attentions for these samples. Secondly, Neither of the loss functions need to consider immense background points, as most of them are already outside of the predicted spherical sectors, which are hostels causing imbalance problems in existing works. The table shows the quantitative result on ScanNet hidden test set. As can be seen, Spherical Mask outperforms all existing works based on coarse to fine, grouping, corner, and transformer. This figure shows qualitative comparison with existing works in ScanNet v2. Here, the blue and red circles highlight cases where Spherical Mask outperforms the existing works. Thank you for listening. Please refer to our paper for details on the method and more experiments.